Hi friends, welcome to my YouTube channel in Advanced RTL Design Coding. So as you can see on my screen, today we will discuss problem 3 Fibonacci series. We will implement the Fibonacci series into Verilog or system Verilog RTL design code. So Fibonacci series, let's understand what is the Fibonacci series first. So it's the Fibonacci sequence is a sequence in which each number is the sum of the two precedent number. What does it mean? So the Fibonacci series start from 0 1. So it's like the initial sequence will be 0 1. The next sequence will be the addition of the last two numbers. So the next sequence, third one, will be the addition of one of the last two numbers, 0 and 1. So 0 plus 1 1, and the 2 will be the addition of last two numbers, so 1 plus 1, and the next number will be the addition of last two number. So last two number before this sequence is 2 and 1. So 2 plus 1 3. So that's how this sequence keep on incrementing. So this is the requirement. Enable the Fibonacci count when enable is set. Parameterized Fibonacci length. Synchronous reset design. So you have to get the input. You like someone need to tell you that when you have to start incrementing your Fibonacci series, your Fibonacci sequence, and till when you have to increment that, what Fibonacci length will tell, and design will work on the synchronous reset. So the design will reset when clock is active. So suppose you are working on pulses of the clock. So when reset is asserted at the pauses of the clock, your design will be reset. So that's how the synchronous reset works. So uh, without wasting much time, let's move to the RTL code. So this is the module name Fibonacci, and Fibonacci length parameter I am passing as a parameter. So current value is 32. You can keep whatever value you want based on the what is the maximum number it will support into 32 bit. You can increase the data width also. So you can parameterize data width as per your requirement. As of now I am keeping it 32, and enable will tell when to start your Fibonacci sequence. So I have taken two registers here, previous value and current value. So your Fibonacci series will be the addition of your previous value and current value. So next, to generate the next number, you have to get the previous and current value so that you can generate the next number. So that's how I have declared two registers, and this is count to count how many numbers of Fibonacci length you want. Okay, so at the pauses of clock, so I'm writing this RTL code into the system Verilog. You can write into Verilog or VSTL. So in the Verilog, you don't need to write always underscore ff. It's a kind of same. Uh, it will behave same like always at the rate for pauses clock. So here I will initiate the value. So as uh, it is defined in the definition of the Fibonacci series that the sequence commonly starts from 0 and 1. So 0 and 1 are the initial values. So that's I'm initializing the previous value 1 and the current value is 0. So current value will be the value that will assign to your Fibonacci output. That's why I'm keeping it a current value. So when enable is high and your count is less than the Fibonacci length, then at that time you have to assign the current value in the Fibonacci length, Fibonacci output, and the current value you should assign with the previous value, and previous value should be increment by the current value plus previous value. Okay, or you can say this is the next value, and the count equal to count plus 1. So when like there's no count, when count reached to 32 or there is no enable, so again you have to restart your sequence. So again you will need to give the reset value or starting value, that is like the default value of the Fibonacci series. And here is the test bench. So it's a very simple test bench where you will instantiate your module. You can see from line number 46 to 53, that's where I have instantiated my Fibonacci module. And here it's like I'm initiating the clock, and here you have to generate, I have generated the clock for 10 nanosecond. So at every 5 nanosecond it will revert the value, so the clock will generate for the time period of 10 nanosecond, and that's how the enable and reset you will need to generate. Let's see the waveform. So you can see when enable started from this clock cycle. Here enable is started, but it's a negative is, but we are working on pauses. So enable is started from here. So your first output will be this one. So here this at this clock your input output is 0, and at this clock 1, and at this clock again 1. So 1 will be high for 2 clock cycle, then 2, 3. So you can see the last two number 2 uh, and 1 is added to get the next number, that is 3. And at this clock cycle you will add the last two number 3 and 2 to get the 5, and 5 3 8, 8 5 13, 13 plus 8 21, 21 plus 13 34. So that's how it will keep on incrementing and generate the Fibonacci sequence. You can see the counter is also incrementing, and once it's reached to 32 it will reset to 0. So here the counter is 0, so your sequence is again initiated with the 0, and at the next clock cycle it will again start incrementing. So 0 1 1 will be held for 2 clock cycle, because the sequence is like we get the 2 times 1. So 0 1 1 2 2 1 3 3 2 3 plus 2 5 5 plus 3 8. So that's how the sequence is generated. So that's all for Fibonacci series. Thanks for watching my video.